Hi, my name is Harun Shafiq and I am an associate design engineer at Lampro Mellon. Currently, I am working on design verification environments for RISC-V based processors. In this video, we will see the complete flow of LM RISC-V DV environment. It is an open source design verification environment which integrates SweRV core from Western Digital and Google's RISC-V DV as a random test generator. We will quickly go through the repository structure and then we will see the files and modifications required for integration of SweRV in this environment and its structure with the integrated SweRV. We will then go through with each step explained in detail. So this is the link to LM RISC-V DV repository on GitHub. The top level hierarchy of the environment is shown here with purple colored blocks representing the empty folders and blue folders contain some files. The text included in pink boxes with dashed outline represents files within a folder. Scripts contain two files. Core integrate.sh is the script which clones the SweRV core and Google RISC-V DV, checks out to the latest tested commit versions and then integrate the core into this environment. And the toolgen paths script lists some paths variables which are needed for compiling the test. Docs directory also contains some files but are not shown here just for keeping the structure tidy. Next we will discuss the integration files directory in detail. This tree diagram shows all the files used for integration of SweRV with Google's RISC-V DV. Since Google RISC-V DV is a random assembly test generator and random tests cannot cover some specific scenarios, therefore one may need directed test. Those tests will be placed in directed tests directory. Some of the scripts and sources from Google RISC-V DV are modified specifically for SweRV LM RunPy and LM CurvePy scripts generate and execute commands for test generation, test compilation, spike simulation, and extraction of functional coverage. The main source file which generates the assembly file is RISC-V ASM program gen. In Google's RISC-V DV, all the code sections are generated from this file. For SweRV exception and interrupt handler routines are customized in this file. For mapping memory regions from test to SweRV memory map, regions are defined in RISC-V instruction gen config file. Google RISC-V DV generates CSR test from gen CSR test.py script. And the modifications for post simulation comparison are done in instruction trace compare and spike log to trace CSV. Files under RISC-V DV extension folder are really important for generating tests specific to the core architecture. Key options like registers length, supported privilege mode, supported IS extensions, unsupported instructions, etc. are set in RISC-V core setting. Testlist.yaml lists all the directed and random assembly tests which can run on SweRV from this environment. If you add more directed or random tests, then extend testlist.yaml accordingly. Link.ld is the general linker script used during test compilation. However, there are some linker files specific to the test. For example, RISC-V load store instruction DCCM test.ld contains memory mappings specific for DCCM regions. Core log to trace is used for converting the execution log from tracer into a specific format in CSV file. SweRV is a configurable core which comes with some predefined configurations. For now, we are using default configuration from SweRV. Defines file for RTL, testbench and directed tests are placed in snapshots directory. SweRV does not come with a tracer. We have implemented the tracer well enough which is required for functional verification in post-sim comparison. So testbench directory contains modified testbench files along tracer files. YAML directory contains two YAML files. RTL simulation.yaml contains base command for RTL compilation and RTL simulation. whereas SweRV CSR.yaml lists all the CSRs implemented in SweRV EH1. For each CSR, bit fields properties and reset values are defined. SweRV EH1 flist lists all the RTL and testbench files in dependencies order. It is used by RTL simulation.yaml during RTL compilation. SymPy is a Python script similar to LM RunPy and is responsible for generation and execution of RTL compilation and RTL simulation commands and for post simulation comparison. And then we have two files, one of which is cover.config, which is used for defining the top level tree for code coverage, and vcs.tcl is a tickle script used for dumping waves. Both of these files are also used by RTL simulation.yaml. And in the end we have the make file, and it is a single file for running the whole flow. Major targets included are compile, gen, GCC compile, RTL sim, ISS sim, post compare, fcurve and urgcurve. When we run the core integrate.sh script, it copies all the integration files shown in the previous slide to integrated cores directory except one folder. Google DB's modified files are copied to Google RISC-V DV directory in the root directory, whereas RTL files are copied from cores/swerv directory into integrated cores/swerv. So the environment flow begins from RTL compilation and random assembly test generation. These two steps are independent of each other and can be done in any order. After the random assembly tests are generated, they need to be compiled, and binary and hex files are generated, which are then needed for RTL simulation. If you want to run a directed test, then you only need to compile the test. Once the RTL and tests are compiled successfully, hex files are loaded into the memory and instructions are executed on the core. During simulation, execution log is also generated with the help of tracer. Now, for verifying the functional behavior of the core, we need to compare the execution log with some golden reference, which is Spike ISS in our case. On simulating the test on Spike ISS, an execution log is generated but in a different format from tracer's execution log. So before post-simulation comparison, both the log files are converted into CSVs in same format. Both CSV files are compared instruction by instruction and look for update on destination register. If it's same in both the CSVs for all the instructions, then test is passed. Otherwise, it fails, and a log consisting of first few mismatches is generated. These mismatches will help you in debugging the functionality of the core. In the end, we can generate code coverage report and extract functional coverage from the CSV files. Let's go through each step one by one. So the first step is to compile RTL. We use compile target from makefile. For compiling, we do not need any other variable from makefile. MakeCompile runs the SymPy script which calls the compile function. This function reads and generates the command from RTL simulation.yaml and runs it. The compiled RTL is placed in RTL sim folder in output directory. Next we generate some random tests. MakeGen does this for us. It takes the name of the test given in testlist.yaml and optional value of seed. If the seed is not provided, a random value is used instead. Gen target runs LM RunPy, which calls gen function. It compiles the Google DV SVUVM base source and then generates test on simulation. Major tests generated and run on SweRV core for now include arithmetic basics, load stores, CSRs, jumps, branches and loops, exceptions and interrupts test. So the next step in DV flow is test compilation. In case of random assembly tests, they are compiled using make gcc compile. It runs lm runpy which calls gcc compile function. These functions take linker file and if there exists any defined file for compilation. Object files, binary and hex files, and disassembly files are generated within the same folder in which tests were generated. And in the case of directed tests, there are dedicated functions in LM RISC-V for C and assembly test, which are run-C and run-assembly. These functions are actually called before any of the random test flow if they are given as test to the makefile. However, there is no dedicated target for calling these functions from LM RISC-V in makefile. Therefore, we are using gen or GCC compile target. Before reaching gen or GCC compile function in the LM RISC-V, run C or run assembly will have compiled the directed test if there exists any. In case of directed test, output folder for compiled binaries and hex files is directed ASM test or directed C test instead of ASM test, which is for random assembly tests. Up till now, you should have the compiled RTL and hex files from compile test. To run the test on core, we will use RTL sim target with test and seed variables. There are optional variables in makefile for waves and coverage data dumping as well. This target first copies the compiled RTL in the corresponding seed folder. It then runs simpy, which calls RTL sim function. This function copies the hex files from test folders to directory where makefile is present. It then takes the simulation command from RTL simulation YAML and executes it. We have also provided the name for tracer log file in sim command in YAML file shown at the right. All the execution log is dumped to this file. Simulation log and tracer log are generated in RTL sim folder corresponding to each test file within the seed folder. Trace corresponding to each instruction is dumped in the execution log when instruction complete signal becomes high. The output log contains each instruction trace in a single line, with a single line consisting of simulation time, program counter, instruction binary and its decoded string, and accessed registers and memory contents. Once we have a tracer execution log, how do we confirm the correctness of a program execution on core? We need a golden reference for comparison, and this is where Spike ISS comes in. Spike is an ISS developed by the architects of RISC-V and it simulates the test irrespective of microarchitecture implementation. We use ISS sim target along test and seed variables. It runs LM RISC-V which calls ISS sim function. This function takes and executes the command from iss.yaml file present in Google RISC-V DV. An execution log file is generated in Spike sim folder in corresponding seed folder. An example of the Spike ISS execution log is shown at the right. It gives us the core number, PC instruction binary and its string, privilege mode and register and memory contents along their addresses. Up till now, you should have execution logs from Tracer as well as Spike ISS. The most important part of any DV flow is the one which functionally verifies the cores. We are using post-simulation comparison between execution logs obtained from our core, which is SweRV in this case, and golden reference, which is Spike ISS. Post-compare target from makefile is used along test and seed variables. It runs simpy which calls compare function. Since both the logs are not in same format, we first need to convert them into a same format for correct comparison. Compare function first converts both of these log files into CSV files in the same format. These files are generated in the folders in which logs were present. Then instruction by instruction comparison begins. Instruction binaries along the destination register updates are compared. The log of this comparison is generated in regression log file which lists first few mismatches if there exist any Otherwise, it prints a statement showing the tests have been passed. If the tests are passed in post-simulation step, we'd like to find the code coverage. We are dumping the code coverage for line, toggle and branch. Code coverage options can be modified from RTL simulation.yaml. We have two targets for code coverage. One of these two targets gives us coverage for an individual test, and the other results into merged coverage from all the tests run so far in output folder. When you use cov-urg all target, it takes coverage database from all the test folders in output directory and merge the coverage into urg report folder. Whereas cov-urg test target generates the coverage report for specified test and seed folder in the test cov folder in project's root directory. LM RISC-V DV also supports the extraction of functional coverage from CSV data. Functional coverage can be extracted either from Spike ISS CSVs or core CSVs. fcov-sim and fcov-core are the targets in makefile for extraction of functional coverage from Spike ISS and core respectively. Both of these targets run lmcov-py script and dump the coverage databases in the respective seed folders. After that, urg command will generate the functional coverage report from those databases. Cover groups being used currently are present in RISC-V instruction cover group file in Google's RISC-V DV source. You can add your customized cover groups in the mentioned file. It should be noted that generated functional coverage report does not give us any information about the microarchitecture. It only generates the ISA level coverage, which includes coverage of all operands in instructions, arithmetic corner cases like overflow, division by zero, aligned or unaligned load stores, etc. So we have seen all the steps of LM RISC-V DV environment in detail. I acknowledge all the repositories on which LM RISC-V DV is based, and those repositories include RISC-V DV, SweRV EH1 core and IBEX core. Thank you very much for watching this long demo video. If you have any question, you can comment below or reach us via GitHub repository page.